So now we are actually going to start implementing linear regression using Python, and I would suggest that you import and read in all these packages: pandas as PD, numpy as NP, scipy as stats, cbone as SNS. This is especially important as we are going to use the inbuilt iris data set of this particular package. And the special thing about it is that I want you to get comfortable with carrying out statistical analyses and subsequently machine learning on pandas data frame, because essentially that is what you have to do in real life, as opposed to working with inbuilt data sets which are not present in the data frame format, because working with those data sets will not equip you to handling pandas data frame type of data. Then after that, you can read in statmodels.api as SM, and stats models, that is a very important package for statistical modeling in Python. And we are also going to use sklearn, and from there we'll import linear model. I'll just briefly touch on what sklearn can do for us in terms of linear regression, but let's just get started with the data. So I've read in the data into the pandas data frame. So I've created a variable iris and I've read in the data iris. Now suppose I want to predict the variation in petal width y as a function of the variation in petal length x. So in this case, y is my response variable, and my implicit assumption is that petal width depends on petal length, and I want to see what is the relationship between them. So this is my response. This is the predictor. Basically, I want to use the predictor to predict my response variable, and I'll carry out linear regression, and I'm going to call sm.ols, and this comes from the stats model package, sm.ols y comma x. So whichever is my response variable is going to be y, that comes first, followed by x, which contains my predictor. And when we just have one x, the way we do in this situation, that is known as linear regression. And I'm going to get the results on the model.fit, and then let's just get the summary. So the dependent variable is the petal width. We already established that. And petal width or response variable are the same thing. Since we just have one predictor, I'm going to report the R square, which is the same as adjusted R square in this case. R square is 0.967, and this means that this particular model, which is actually stored in the variable model, explains 96.7% variation in petal width. So remember, that is how we interpret R square or adjusted R square. And this particular number, basically this explains the variation in our y. So 96.7% of variation in y is explained by model. We will look at prob, which is the probability. And if this is less than 0.05, which it is, the model is statistically significant, and I can therefore report it. And this is the coefficient of my petal length, the beta value, and this is 0.3365. I'm not going to discuss these right now, that will come later. But now, where is my intercept info? So if I want the intercept, I'm going to again create my x, and now I'm going to use the numpy to add a constant row for the intercept, and it's the petal width. So I'll again fit the model the same way, and as you can see, I have x1 is, well, I get the same things like adjusted R square, which is 0.92, so which means that this model explains 92.7% of the variation in petal width. The model is statistically significant because the p-value is less than 0.05. I will explain what the other things mean later on, but the upshot is that the x1 or the intercept value has been produced, which is 0.41. Since the p is less than 0.05, it's just 0, and the constant, the slope value 0.363 is also less than 0.05, we can say that the intercept and the constant, they're both the intercept and the slope, they're both statistically significant. So basically, this is the relation, this is how we formalize the relationship between petal width and petal length, 0.41 minus 0.36 into petal length. So essentially, if I go out ever again into the field and measure petal lengths, then I will substitute them into this particular equation to get an estimate of the petal width. And yes, the petal length and petal width are associated with each other. And essentially, this is how we model the relationship between two using linear regression. And linear regression just produces the equation of a straight line which connects my response variable with the x. But then what happens when I want to predict my y in terms of, say, more than 1x? So, previously I just looked at petal length, but now I want to explain the variation in y, petal width, in terms of petal length and sepal length. I can do that. Over here I'm going to create my predictors, and now I have two predictors, which makes it a multiple regression problem. So I have two predictors. They have been created and stored in variable capital X. Now, in order to get the constant, I'll say sm.add constant, but x. I will not put the 2 over here, and this adds constant row for the intercept, y. Then I'm going to call model sm.ols for ordinary least squares, yx. Results model.fit, and now this is what I get. Now when I have more than one predictor, instead of r square, I report adjusted r square, and this means that this particular model with two predictors explains 92.8% variation in petal width. And now this is the constant or the intercept, and petal length and sepal length, these coefficients are the values of the slopes of petal length and sepal length. Since in this case, for the constant, my p value is greater than 0.05, my intercept is non-significant, and when I want to create an equation, I will not report the intercept, but my betas or the slope coefficients are statistically significant because they are both less than 0.05. Thus, I will be reporting those. And essentially, the most important thing, well, over here, again, adjusted r square, my overall p-values are less than 0.05, which makes my model statistically significant. And essentially, this is how I can report an equation of the straight line when I have more than one predictor. Now, I can even use categorical variables, and my categorical variables are going to be species. And as you can see over here, I've assigned numerical values to the different species. Over here, setosa is 1, others are 0, and so on. So now my X is going to comprise of petal length, sepal length, setosa, versicolor, virginica, and all of these are categorical variables which have numerical values assigned to them. I did that using pd.concat, and I already got the dummy variables. So basically, when we want to work with categorical variables, we end up doing dummy variable regression. So pd.getDummies is going to basically assign numerical values to my categorical categories of setosa, versicolor, virginica, and these are my dummy variables in a manner of speaking. And then I'm going to concatenate all of them together like so. So this is my data frame that I will work with now, and I will add in setosa, versicolor, virginica as my other normal predictors. The same thing to get an intercept. Then I'm going to fit the model sm.ols y capital X. And now, as you can see, the model is statistically significant. The p-value is less than 0.05. This is the adjusted r square, which is 0.944. And as you can see, these are the beta coefficients associated with my predictors. So the constant value is statistically significant, but sepal length is not because p is greater than 0.05. And the same goes for versicolor. but the other two categorical variables are statistically significant, which means that the species, or at least the fact that Virginica and Setosa, they have a significant impact on determining petal width, whereas versicolor doesn't, and that is what it means. And I can just create the equation of a straight line using all of these coefficients, and I will only include the coefficients which are statistically significant. And then I can even fit a linear model using sklearn. So I just fitted the first linear regression model, saying linear model dot linear model, and I define the model, and my results, I'm going to call them model dot fit xy, and these are the intercept and the coefficient values. And essentially sklearn is not the best thing to use for linear regression, but we are going to work a fair bit with sklearn in the next couple of sections. But here's, this is how we use stats model for carrying out linear regression, both linear regression, multiple linear regression, and actually using categorical variables or dummy variables.